Welcome students. Today topic is dielectric. In the previous class, we have learnt about the grouping of capacitors in series, in parallel and the numericals based on it. Today, we will study about the dielectric. Before dielectric, all of you know that substances can be classified into three categories. The first one is conductors, the second one is insulator, and third one is semiconductors. Conductors means whose conductivity is very high. They have a large number of free electrons. Insulators which do not conduct electricity. Conductors conduct electricity because their conductivity is high. They have free electrons. Insulators, they do not have free electrons. Therefore, they do not conduct electricity. Semiconductors, their conductivity lies in between conductors and insulators. Now the topic is dielectric. What is dielectrics? Dielectrics are, simply we can say, all the insulators. Therefore, they do not have free electrons at room temperature. In other words, we can define dielectric also as these are the insulating materials which transmit electric effect without actually conducting electricity. Without actually conducting electricity shows that they do not have free electrons. Now there are two types of dielectrics. The first one is known as the non-polar dielectrics. Non-polar dielectrics, and the second one is known as the polar dielectrics. There are two types of dielectrics, non-polar and polar dielectrics. What are the non-polar dielectrics? In these dielectrics, the center of the positive charge, that means in the nucleus there are neutrons and protons. Protons are positively charged. They are concentrated in the nucleus, and the electrons are revolving around the nucleus. They have negative charge. So the center of all the positive charges and the center of all the negative charge, that means electrons, they coincide with each other. You can say in this case the shape of the atom or molecules is spherical in shape. This is the center of the positive charge as well as this is the center of the negative charge. In the non-polar molecules, the center of the positive charge and the center of the negative charge coincide with each other. They are spherical in shape. Examples of non-polar molecules are nitrogen, oxygen, hydrogen, carbon dioxide. There are other examples also. What about polar molecules? In these polar dielectrics, the center of the positive and negative charge do not coincide with each other. The center of the positive charge is lying at a different place that of the center of the negative charge. In this case, the shape of the polar molecules, you can say elliptical in shape. This is the center of the negative charge. This is the center of the positive charge. One end is negative and the other end is positive. That's why they are known as the polar dielectrics. The examples of this one is H2O, that means water, ammonia, NH3, hydrochloric acid, HCl. All these are the examples of the polar molecules. Since here the center of the positive and negative charge are coinciding with each other, they do not have any electric dipole moment. Yeah, in other words, we can say electric dipole moment is equal to 0. Electric dipole moment is equal to 0 in the case of the non-polar molecules, or dielectric you can say. But in this case, one end is positive, other end is negative. It is just treated just like an electric dipole. Therefore, it has electric dipole moment. It has electric dipole moment. Because center of the positive and negative charge do not coincide with each other. Once again, I am repeating here that what are the dielectrics? Dielectrics are the insulating materials which transmit which types of effect? Electric effects without actually conducting electricity. That means they do not have free electrons, therefore no electric current can flow through it. Now the types of dielectrics, there are two types of dielectrics. First is non-polar dielectrics. The second one is polar dielectrics. What about non-polar dielectrics? In these dielectrics, the center of all the positive charges and the center of all the negative charges coincide with each other. Therefore, their electric dipole moment is zero. And the examples of the non-polar dielectrics are nitrogen, oxygen, hydrogen, carbon dioxide. Whereas in the case of the polar dielectrics, the center of the positive and the negative charge do not coincide with each other. One end is negative, another end is positive. Here the center of all the negative charge is concentrated. Here the center of all the positive charge is concentrated. Therefore they behave just like as an electric dipole. One end is negative, another end is positive and separated by a small distance. Therefore it has electric dipole moment. The examples of the polar molecules are water, ammonia and hydrochloric acid. Now what happens when these non-polar molecules you can say is placed in an external electric field? What is the effect of the external electric field when it is placed in it? I am showing only one molecule is here. So what is the effect of the external electric field? This is your non-polar and this is your polar. Non-polar, non-polar and this is your polar. This is your polar. So what is the effect between these two by placing it in the external electric field? Then what happens? Thus positive charge is pulled in the direction of the electric field and the negative charge is pulled in the opposite direction of the electric field. In general you can say here, suppose this is an external electric field which is applied between these two plates. This end is you can say positive, this is your positive plate and this is your negative plate. The same positive and negative charges should be there. This is your negative plate. Positive plate and negative plate, and this is the slab of the dielectric which is placed in between these two plates. This one, slab of the dielectric. Now here it consists of non-polar molecules. Then what happens? Suppose I am showing here in a row only two molecules are there. This is your one molecules, this is another one, third one, similarly fourth one you can say, similarly fifth one. I am showing these types of molecules. Now the in the previous, when the no electric field is applied, what is its actual situation? It is in this way, spherical in shape when no electric field is applied. This one, and the positive and negative charge are coinciding with each other. Now what happens when external electric field is applied? The positive charge are pulled in the direction of the electric field. What is the direction of the electric field? From the positive plate to the negative plate. That means This end is your positive, this is positive, this is positive, this is positive, positive charge, and this end is negatively charged, this one, because they are moved in the opposite direction of the electric field. That means in this direction. यानी कि first negative charge come and at the second end positive charge comes. Now what happens? Now this negative charge is bound to this positive charge due to the force of attraction. Similarly, this positive charge is bound with this negative charge due to force of attraction. The charges which is lying in between this one, these two layers of charges cancels each other effect. Then what happens? Then the resultant effect is this plate is positive as the external electric field is applied. This plate is negative and the dielectric slab which is placed in between these two plates, this end becomes negative and this end becomes positive. Now a net electric field is developed inside an dielectric and its direction is from positive to negative, this one. This is the direction of the polarized electric field. And in the initially case, when no dielectric slab is placed, the direction of the electric field is in this, from positive to negative, in the absence of the dielectric slab. Now you can say that when a non-polar molecules is placed in an external electric field, it becomes a polar molecule because center of the positive and negative charges are pulled by the external electric field. Initially, when no external electric field is applied, no electric dipole moment is present here. But in this case, when the external electric field is applied, they acquired a induced electric dipole moment. Each molecule of non-polar dielectrics becomes polar molecules, and the charges which are inside the slab, they cancels each out, but the charges which are present on the faces which are towards the positive or negative plates remains as such due to the force of attraction between the face and the charge on the plates. Okay, this is the induced electric dipole. Its moment is known as the induced electric dipole moment, and the phenomenon of producing the induced charges on the opposite faces of the dielectric slab is known as the polarization. This means the charges are inducing on the faces of the dielectric by the process due to which these charges are induced on the dielectric. This process is known as the polarization. But when the polar molecules is placed in an external electric field, only in an absence of the external electric field, they are aligned in different direction, you can say, so that their net electric dipole moment is 0. Suppose this is negative, this is positive. Now in the second case, this is positive, this is negative. These two cancels each other effect. Similarly, they are randomly oriented, you can say. This is negative, this is positive. You can say this is positive, this is negative. They cancels each other effect. In the similar case, this one minus plus, you can say this one plus minus. All these cancels each other effect. The net electric dipole moment when a polar dielectric is placed between the plates but there is no electric field. That means two plates are present there but there is no charge on the plates. Then the net electric dipole moment is equal to 0. What happens when a polar molecule is placed in an external electric field. Only the difference is that this is your positive plate and this is your negative plate. They aligned in the direction of the electric field in this way. Only the difference. They all molecules are the polar molecules, but in the absence of the external electric field, they are randomly oriented. Due to randomly orientation, their net electric dipole moment is zero. But when the external electric field is applied, so only the difference is that they are aligned in the direction of the electric field. They have a net electric dipole moment. No new electric dipole moment is induced in these molecules. Therefore, they are not so much importance. In the dielectrics, we use only the non-polar molecules because in the absence of the external electric field, that electric dipole moment is zero. Each molecule has no electric dipole moment, but when they are placed in an external electric field, each molecule acquired a value of the electric dipole moment. They become a electric dipole. This dipole is known as the induced electric dipole and their moment is known as the induced electric dipole moment. Therefore, the importance of non-polar molecule is much more than that of the polar molecules. Now, there is a term that is, dielectric constant, and this dielectric constant is defined by, in the terms of the induced electric field and reduced electric field. Now, inside the dielectric, suppose electric field is this one, and when these are placed in the external electric field, this one, this is negative, this is positive, and the external electric field means this is positive and the other one is negative. So what is the value of the electric field inside the dielectric? In the absence of the dielectric, the electric field is E naught and its direction is from in this way. Now, when the charges are induced on the opposite faces of the dielectric, the induced electric field, that means polarized electric field, is this one and its direction is opposite to E naught. Now, what is the net value of electric field inside the dielectric? यानी कि net electric field inside dielectric, what its value? You can say both are the vector quantity. The net is the vector sum of these two quantities, E naught plus EP vector. Naught shows that there is no medium, there is air. And P means when the dielectric is introduced between the plates. Now both electric fields are in the opposite direction. Therefore, in magnitude you can write here E is equal to E naught minus EP. This is known as the reduced value of electric field. Reduced value of electric field. That means E. Reduced value of electric field. How can you define the dielectric constant? The dielectric constant is denoted by capital K. That means capital K is equal to E naught upon E. Or you can say dielectric constant is the K means is the K is the ratio of this is applied electric field to applied electric field to reduced value of electric field to the reduced in the terms of the electric field to the reduced value of electric field. This is the definition of dielectric constant in the terms of the electric field. You can define it in this manner. In the first chapter, all of you know that we define K as, in the first chapter, we define K as K is equal to epsilon upon epsilon naught. Okay, this is also equal to F naught upon F, and this is equal to, now that is equal to E naught upon E. In any manner you can define the value of the dielectric constant, and you can substitute the value, get the value of K here. Suppose you know E naught. What is E naught upon, due to the point charge, you can say here 1 upon 4 pi epsilon naught Q upon R square. Here the vacuum or free space is there. Now in the terms of the medium, you can say here 1 upon 4 pi epsilon naught K. K is the dielectric constant. Q upon R square. All these cancels out and we get here K. Similar is the case of the force also. And epsilon naught upon epsilon upon epsilon naught. This is also equal to K. This topic is very important. Now we will calculate the capacitance of a capacitor with a dielectric slab between the plates, and the thickness is different than the distance between the plates. Now the next topic is capacitance of capacitor with a dielectric slab between the plates. Then how can you determine here? You can see here capacitor of a capacitance between the plates. Now suppose you can understand here very clearly that a dielectric slab is placed between the plates. Then what happens? This is your plate, first plate. This is your second plate. Parallel plate capacitor is there. This plate is positively charged. 3, 4, 5, 6. Here also 6 minus is there. Now a dielectric slab is placed between the plates, this one. Then what happens? We have to determine the capacitance. Its thickness is not equal to the distance between the plates. Yeah. Here you can say thickness T is less than D. Here आपका T is less than D. What is T? T means thickness of the dielectric slab. You can see here this distance is T. This is thickness, and from this to this distance is D. Distance between the plates. Then T is less than D. What is the value of the potential difference between the plates? Potential difference between the plates. How can we determine its value? Now, D, in the absence of the dielectric slab, D is in air. Now, T is in dielectric slab. Which portion is in air? Only this and this portion. How this and this portion can be determined? By subtracting T from distance D. Then we get this plus this portion which is in air. And you know E is equal to V upon D. This is a relation. Or you can say V is equal to E into D. You must know the value of the electric field and the distance in the air and in the dielectric. Then simplify it, you will get the answer. Now it is denoted by V. V is equal to, now which portion is in the air? In air the thickness is d minus t and the electric field is E naught. That means E naught d minus t plus, what is the value of the electric field inside the dielectric slab? Reduced value. You can say E and the thickness is T. This is in the air. This thickness is in the air. This thickness is in dielectric. This electric field is in dielectric. Now, in the previously I have studied that K is equal to, what is the value of K? Is equal to E naught upon E. That means E is equal to E naught upon K. Substitute the value of E directly from here. You can get here E naught d minus t plus E naught upon K into T. Now E naught comes outside the two terms and we get here d minus t plus t upon K. What is the value of E naught between the plates? You know, sigma upon epsilon naught. Two parallel plates, sigma upon epsilon naught d minus t plus t upon K. And what is sigma? Sigma is the surface charge density, charge divided by area. Therefore, we can write here charge, that is your Q, area between area of the plates, that is A, epsilon naught within bracket d minus t plus t upon K. This is the value of the potential difference which exists between the plates. This is your first equation. Now you know what is the value of C. C is equal to, as per definition, C is equal to Q upon V. This is your, suppose, second equation. Now substitute the value of V from equation 1 into equation number 2. Then what happens? We can write it here from equation number 1 and 2. You get here, your value is C is equal to Q. Substitute the value of V. V means Q upon A epsilon naught within bracket d minus t plus t upon K. Now Q cancels out. This comes in the numerator. We get here C is equal to A epsilon naught and in the denominator d minus t plus t upon K. This is the capacitance of a capacitor when a dielectric slab is partially filled between the plates. Now one question again, I am explaining this topic. What is the potential difference between the plates? Here we have taken that the thickness of the dielectric slab is less than the distance between the plates. What is the potential difference between the plates? As you know the formula, V is equal to E into D. This is the formula. If E is in the air, then D should be in the air. If E is in the dielectric, then the value of D should be taken which is in the dielectric. Here the D previously is in air and T thickness is in dielectric. Then what is the thickness which is in air? That is equal to D minus T. In air, you know the applied electric field is E naught. Therefore, the first term is E naught, thickness in air, T minus T plus. Now, what is the value of electric field inside a dielectric? That means the reduced value of electric field, which is denoted by capital E. This is your capital E. And the thickness, that is equal to T. Now, what is the value of E in the terms of E naught? As we know that K is equal to E naught upon E. From this implies that E is equal to E naught upon K. Substitute the value of E here directly. Now from these two terms, E naught comes outside the bracket, and within the bracket we get d minus t plus t upon k. And what is the value of E naught? An electric field between the plates in the air, that is equal to sigma upon epsilon naught. And what is sigma? Sigma is the surface charge density, charge divided by area. That means Q upon A, and this is the value of the potential difference between the plates. As you know, C is equal to Q upon V. Substitute the value of V from this equation into this equation. We get here Q cancels out. A epsilon naught comes in the numerator, and the denominator we get here this one. This is the required expression for the capacitance of the capacitor partially filled with dielectric slab. What happens when thickness D and T becomes equal to each other? That means if D is equal to T, in this case, when D is equal to T, what happens? C is equal to A epsilon naught D minus D plus D upon K. D cancels out. We get here, and K comes in the numerator, K A epsilon naught upon D. You can write it here, K, C is equal to K within bracket A epsilon naught upon D. What is A epsilon naught upon D? Capacitance of the parallel plate capacitor in vacuum. This is represented as C is equal to K C naught in vacuum. This means when the capacitor is filled completely with a dielectric, then its capacitance increases K times. That is the end of this lecture. Study it with practice it in writing 2 or 3 times. This is very important for the board examination, and the numericals also comes from this topic also. Okay, bye.